So welcome to the afternoon session. I'll give the speakers a 5 to 10 minute warning so that we have a little bit time of discussion. The first speaker will be Santosh Das, and he will give us an overview on open heavy flavor. Santosh, why don't you share your screen?
Sure, thank you. Is it visible now?
Yes, it is.
Thank you. Should I start?
Something, but we cannot hear you.
Okay, so should I start? I have yet to start. Should I start now?
Yes, please start.
More explicit.
Okay. So good morning, good afternoon, good evening. First of all, I would like to thank the organizer for organizing such a nice conference in hybrid mode, and of course for the invitations. So today I will mainly discuss about the theory overview on open heavy flavor, and my major focus will be hadronic diffusion of charmed hadrons and its possible contribution to experimental observable related to the topic of this conference. So this is the outline of my talk. First, a brief introductions on heavy quark diffusion in QGP. Then I will move to heavy meson diffusion in hadronic matter. Then the impact of hadronic phase on heavy quark observable. Then I will just highlight the possible impact of pre-equilibrium phase. Finally, a summary and outline. So as we know, these heavy quarks are considered as a novel probe to characterize the QGP. This is because due to their large mass, mainly the charm quarks and bottom quark, due to their large mass, they are produced in the early stage of the heavy ion collision during the hard scattering. So they are the witness of the entire phase space evolutions of the QGP. Also, their mass is much larger than the temperature of the medium. So thermal production will be suppressed and their number will remain almost conserved. Also, the relaxation time of these charm and bottom quarks are much larger than that of the light quarks and gluon. So they act as a non-equilibrium probe, and the momentum evolution of this charm and bottom quark in QGP can be studied within the Fokker-Planck approach. And one can derive this Fokker-Planck approach from the Boltzmann equation on the small momentum transfer. That means if we define the omega pk is the rate of collision, we change the charm quark momentum from p to p minus k, then we can expand the collision term in terms of a loss and a gain term. And if we expand the gain term, the first term around the momentum transfer and keep up to the second term, then we'll arrive with the Fokker-Planck equations. And here this A is the drag coefficient, Bij is the momentum diffusion coefficients. And this drag and diffusion coefficient contain all the macroscopic details how the heavy quark interact with the QGP medium. And here is what we want to study on heavy quark at a different momentum scale. At the low momentum, we want to constrain the heavy quark diffusion coefficients. And at intermediate momentum, we want to constrain the hadron wave function, and for which you want to study the hadronization process of heavy quark. And at a large momentum, we want to constrain the jet transport parameter, and we want to study the energy loss. But to study the heavy quark dynamics in QCD matter is quite involved process. It's complex. To build a realistic model to study heavy quark dynamics in QCD matters need several ingredients starting from its production until it reaches the detectors. That means soon once the heavy quark produced in the hard scattering initially, then the initial state effect like the shadowing, then the pre-equilibrium phase, electromagnetic field produced in high energy heavy ion collision may affect it. Then after the pre-equilibrium phase, the heavy quarks enter in the QGP phase. And in this QGP phase, this heavy quark interact with this QGP medium. We need to model it. Also, we need a evolution equation to study the time evolution, the momentum evolutions of this heavy quark momentum, maybe Langevin, Boltzmann, model based on energy loss. Then once the temperature of this QGP phase goes below the quark hadron transition temperatures, then they will hadronize, maybe by fragmentation or fragmentation plus coalescence. Then they will enter into the hadronic phase where these heavy mesons, the B and D meson, they will interact with the thermal bath, consist of lights, mesons and baryons. So it's indeed an involved process. And in this talk, I will mainly concentrate on the hadronic medium possible impact on several experimental observables. But before that, I will just like to mention to study the heavy quark dynamics in QCD medium, we need to develop, usually we develop several models based on different transport setup for which transport coefficients are usually the inputs. Then we solve the transport equations, compare our model result with the experimental observable. Then we extract the transport coefficients, and at the end of the day, we compare the transport coefficients with the lattice QCD result. So in fact, heavy quark have the potential to relate phenomenology with the experiment and then with the theory. And this experimental result or data provides us constraint on several models, and it provides a constraint on the heavy quark diffusion coefficients. But simultaneous study of this RA and V2 is a top challenge almost for all the models. And here the time evolutions of this nuclear suppression factor and V2 have a different dynamics. That means, as we can see, the nuclear suppression factor is something which is very sensitive to the early stage of the evolutions or the collisions, where the energy density is very high and collision take place at a higher rate. So as you can see, within a one Fermi is almost developed 50% of the suppressions. Then the nuclear suppression factor gets saturated almost at 4 to 5 Fermi. But if we look at the dynamics of this V2 is quite sensitive to the latter stage of the evolution. This is because initially, soon after the collision, the bulk does not have any V2. First, the bulk will develop its own V2, then it will transfer the V2 to the heavy quark due to the bulk heavy quark interactions, which usually happen at the latter stage. So here, the dynamics of these two observables are quite different. One is very sensitive to early stage, one is very sensitive to the latter stage. So from here, we can also, it's give indications. If we will include a hadronic phase after the coagulant plasma phase, the RA may not be very sensitive, because as we can see, the RA almost getting saturated within the QGP phase. It might have a very mild effect, probably, which we will discuss more detail in later. But if we look at the V2, which is very sensitive and which is mainly developed in the latter stage of the evolution, it might be affected significantly by the presence of a hadronic phase. And also here the temperature dependence of the interactions, of the temperature dependence of the transport coefficients, mainly the drag diffusion coefficient, plays significant important role to understand both this array V2 simultaneously. This is because these two observables are related to the different end of this heavy ion collision. One is more sensitive to the early stage, another is more sensitive to the interaction state in the latter stage. And here I just want to summarize the build-up of V2 at a fixed array. That means as we have this, that means this V2 is very sensitive to the temperature dependence of the interactions. Depending upon the temperature dependence of the interactions, the V2 can be much larger, maybe a factor 2.5 or so for the same array. Then again, the V2 will get another boost. What kind of transport equations we are using, whether it is a Boltzmann or it is a Langevin equations. Then again, the hadronization by coalescence will get another boost. Then of course, at the end, it is the hadronic phase. So it is indeed quite complex, but several advances have been made over the year to understand both the array V2 at a RIC and LSC or at a QGP with zero chemical potential. And here there are several attempts to extract the transport coefficient in QGP medium. That means systematic attempts are going on within the EMMI rapid reaction task force and the JET heavy quark working group to find a common agreement between different groups. But here mainly the focus is on the QGP phase to extract the heavy quark transport coefficient at QGP phase with zero varying chemical potential, mainly at RIC and LSC, and usually people ignore the hadronic phase contributions, which will. But as we know, once the temperature of this QGP phase will decrease and goes below to the quark hadron transition temperatures, then this heavy quark will hadronize, be it through fragmentation or fragmentation plus coalescence, then they will enter into the hadronic phase. So the presence of hadronic phase is inevitable in high energy heavy ion collision, but people usually ignore this impact of the hadronic phase at RIC and LSC energy, considering the fact that the interaction strength in hadronic phase may not be enough to alter the momentum distributions or elliptic flow, usually neglect. So first in 2011, Mikko Lane computed this heavy quark, the diffusion coefficients in the hadronic phase consisting of a hot ions within the heavy meson chiral perturbation theory, but they mainly concentrate in the low temperature domain, 30 MeV to 80 MeV. Then the Texas group led by Ralph Rapp, they come up with a phenomenological model based on the empirical scattering amplitudes of the D and the D star with the different light hadrons, and they compute the heavy quark diffusion coefficients in this QGP phase. And the magnitudes are quite substantial and it may affect the experimental observable. And the same times, the Kolkata group, they also computed this heavy meson diffusion coefficients in the hadronic phase within effective Lagrangian approach. And they also computed the heavy quark diffusion coefficient within the scattering length approach as well. Then the Madrid group come forward and they computed the heavy meson diffusion coefficients within the unitarized heavy meson chiral perturbation theory, and they did a series of publications in these directions and explore and go for the variance to compute the heavy quark drag and diffusion coefficients. And here is a comparison of the drag coefficients of the D meson in a pionic gas obtained within different models. So as we can see in this model, the drag coefficient obtained by this Texas group for the D pi interaction, the magnitudes of this D meson drag coefficient in the hadronic phase are quite comparable to the drag coefficient obtained within the unitarized heavy meson chiral perturbation theory. However, if we compare the magnitudes with the drag coefficient obtained within the effective Lagrangian approach, then as we can see, it's order of magnitude larger than the value obtained in the unitarized heavy meson. And here is a comparison among all these four models at 100 MeV temperatures. And here it is a comparison of these drag coefficients for the B mesons obtained within the unitarized heavy meson chiral perturbation theory as well as obtained within the scattering length approach. So as we can see, the transport coefficient computed within the scattering length approach are quite close to the value obtained within the unitarized heavy meson chiral perturbation theory. And here is a comparison for the drag and diffusion coefficients of the lambda C, D meson, lambda B, and B are all these open heavy mesons and baryons. So as we can see, so this unexpected, as we can see, the lambda C drag coefficient in the hadronic phase are quite close to the value of the dimensions drag coefficient in this hadronic phase. And this unexpected similarity can be understood from the kinetic theory expressions at non-relativistic limit, as I mentioned here. As we can see, the drag coefficient in the non-relativistic limit in this within the kinetic theory approach is directly proportional to the cross sections and inversely related to the mass of the hadrons. So if we compare the cross sections and mass of this lambda C and D, this lambda C mass is larger than the D major mass, whereas the lambda C cross section is also larger than the D majors. At the end of the day, their transport coefficients, their drag coefficients are very similar, and which is consistent with this non-relativistic limit of this kinetic theory. And if we similarly compare the drag coefficient, say for D meson to B mesons, they are different here. It is mainly due to their mass difference. And we have also checked taking the ratio between the drag coefficients and their cross section to mass separately. It seems they are quite close to each other and looks consistent. And here is the diffusion coefficient obtained within the same formalism, and here the diffusion coefficient is proportional to the cross sections. So as you can see, for lambda C and lambda B, their diffusion coefficients are very similar to each other. This is because their average cross sections are almost similar, and that's why they are similar. And if we compare lambda C with the D meson diffusion coefficients, here lambda C diffusion coefficients are larger, mainly due to the average cross sections of the lambda C is larger than the D meson cross sections. And if someone will take a ratio, then these are really close and looks consistent with this non-relativistic kinetic theory relations. And here, first, this Texas group, they have computed the special diffusion coefficients within the Einstein relations for both this Platonic phase as well as the hadronic phase. And they observe a continuous evolution of these special diffusion coefficients through the transition region with a minima near TC. This is very interesting, and it is in the same line of eta by S in the hadronics or in the bulk sectors. And this special diffusion coefficients is a mass independent quantity, and this tells a scale with the inverse of the interaction strength. And we later extended the same thing to computing the special diffusion coefficients for lambda C as well as lambda B, and here also we observe a similar minima near the quark hadron transition temperature. Then Laura Tolos and Juan Torres Rincon, they come forward, they have extended their calculations of these drag coefficients of these D mesons from a zero baryonic chemical potential to finite baryonic chemical potential within their heavy meson chiral perturbation theory with the unitarized approach. So as you can see, they have computed both with the zero chemical potential, with the finite chemical potential. So they observe for finite chemical potential, the baryonic contributions can be large, and as you can see, this can even up to a factor 2, and this will be very relevant for this topic of this conference. And in the meantime, this Frankfurt group as well as Nanette combinedly, they have extended this special diffusion coefficients plot from zero baryonic chemical potential to a finite chemical potential within their dynamical quasi-particle models. In this dynamical quasi-particle model, they have also considered the finite chemical potential. Although their initial motivation was to reproduce the lattice QCD equation of states with zero baryonic chemical potential, but later they extend to finite. Although lattice equation of state is not known at finite chemical potential, but they assume the energy density is independent of the baryonic chemical potential. Maybe in this session, they should talk more about their calculations. But after that, first Texas group, they computed the nuclear separation factor as well as the elliptic flow for both this D meson as well as D meson, considering this hadronic medium interaction. That means soon after the QGP phase, after the hadronization, they have included the hadronic medium contributions. And they observe, as expected, this nuclear suppression factor is not very sensitive to the hadronic medium. This is because, as we discussed earlier, this array gets saturated once the radial flow set. So hadronic medium may not affect the nuclear suppression factor. However, they observe the impact of hadronic phase on this D meson elliptic flow is about 30%, as we can see from this plot. It's quite interesting, and they also come up with a very nice idea how we can characterize these hadronic medium contributions, or how we can distinguish this hadronic medium contribution, if any, and that can be done through the V2 splitting between DS and D mesons. This is because soon after the hadronization, the D meson may decouple from the system due to its less interactions. However, the D mesons will couple with the hadronic phase and develop further V2. So whatever the V2 difference between the D and DS, that V2 splitting will act as a promising measure of the transport property of this hadronic phase. Similarly, if we look at this nuclear suppression factor at array, whatever difference we will get in terms of their array from D to DS, it's mainly due to the hadronization, effect. So that also one can probe with a systematic measurements at a low or high energy collisions, how the hadronization also differ. And they also extended the same model to study the nuclear suppression factor and elliptic flow at LHC energy. And here also, as expected, they find the nuclear suppression factor, the impact of hadronic medium is quite mild, as we can see from this plot. However, the impact of the hadronic phase on the V2 is quite significant, and it seems it is about 20%. So here I want to indicate something interesting. And the same calculation within RIG, the hadronic medium contribution on V2 was about 30%. And here, as we can see, the contribution of the hadronic phase is about 20%. So this indicates the relative contribution of the hadronic phase may increase with decreasing the colliding energy. This is because if you are colliding in low colliding energy, the lifetime of the QGP medium will small in comparison to larger colliding energy. Their hadronic phase may contribute significantly. So then, within the PHST, this Frankfurt group also did a calculations for both this nuclear suppression factor as well as the elliptic flow, considering both this QGP phase as well as the hadronic phase. And in this calculation, for the hadronic phase, they have implemented the unitarized heavy meson perturbation theory, and they compute both the nuclear suppression factor as well as the V2. So as we can see, the nuclear suppression factor impact of hadronic medium is quite mild, expect very central collisions. But if we look at the V2 within this framework, the impact of this hadronic phase is about 40% already at the RIC energy. And here within the Catania group also did a calculations to study the impact of this hadronic phase on heavy quark observable at a RIC and LHC, and here mainly we did this calculation for the lambda C within a fragmentation scenario. The aim was mainly to study the impact of the hadronic phase. So as we can see within this approach, Langevin approach to study the heavy quark dynamics in QGP as well as in this hadronic phase, we observe at the RIC energy, the contributions of this hadronic phase is about 20%, whereas if we look at the LHC energy 5.5, it's quite mild, maybe it is about 15%. But as we can see in all these model, 3-4 model we discuss here, they have implemented the hadronic contribution. The contributions is different from different model. But if we compile all of them and try, then we find all the model calculation indicates at a RIC, the hadronic phase contribution to heavy measure V2 can be around 20 to 40%. And this difference is mainly due to what is the hadron transition temperature we are including in our theoretical calculations. This can affect the results significantly. Some group use 170, some group use 165 MeV, some group using 155. I think this contribute to this larger uncertainty about a factor 2, but every group is more or less agree at weak energy the contribution is about 20% is the minimum cutoff, and the 40% can be up to the maximum depending upon what is the value. And here the hadronic medium contribution is very sensitive to the quark hadron transition temperature we are considering, because that can prolongate the hadronic medium lifetimes or can decrease the QGB phase lifetimes, and accordingly the contributions will play a role. And here is a calculations at a low colliding energy with at finite baryonic chemical potentials, which is very relevant for the topic of this conference. And they have did this calculation within a Langevin dynamics, and they have considered both the QGP phase as well as the hadronic phase. But in their major motivation is to study the variation of the decoupling temperatures. So as you can see, they consider 3 different decoupling temperature. One is 160 MeV, another case 145 MeV, another case 130 MeV, 15 MeV difference. So as we can see, the nuclear suppression is not very sensitive, although some effect is still there, probably 10-15%. But if we look at this V2, this impact of this decoupling temperature is really quite sizable, as we can see from this paper. And here is the some calculations for the heavy quark dynamics at the low colliding energy. And these calculations is done within at a colliding energy 6 to 2.4 GeV. And they have studied both the nuclear suppression factor as well as they have studied the elliptic flow. So as we can see in these calculations, the nuclear suppression calculation obtained within the framework of the PHST, they have studied the nuclear suppression factor at a 62.4 GeV. Although this PhD is very successful at RIC and LSE to study several observable related to heavy quark dynamics at QGP, but in this particular case they underestimate the experimental data, and they are. And similarly, if we will look into the same colliding energy, the calculation of the Texas group, the nuclear suppression factor as well as the V2, then as we can see in the more central collision, they miss the data as the high momentum. And if we look at the comparison to experimental data at the peripheral collision, where they miss the experimental data at the low momentum domain. But here one interesting fact, if we see the V2, both this model, PHT as well as the Texas group, they can able to describe the nuclear suppression factors. So here is the RA puzzle at a 62.4. Yes, of course, here the experimental data, there are a large uncertainty. We cannot tell anything specific, but the indication is there. Some indication is there for sure. And interestingly, here there is no issue with V2. One can able to describe the V2 reasonably well. Rather, we are facing problem to understanding the nuclear suppression factor. So here I would like to remind the earlier discussion, the heavy quark puzzles I mentioned earlier at RIC and LSE energy, which was there since 2006 after the first experimental data. But there the RA V2, the issue was mainly with V2, where due to the different complicated dynamics. But if we look at here, the issue is not V2, rather here is the issue is the nuclear suppression factor. So here already at a 60.2 is indicating something new, probably we are missing, and it is certainly interesting. Then according to the author, yes, the initial charm quark production at this low energy collision is not well known, as well as they have not included the pre-equilibrium phase. This might play some role along with maybe some other effect as well. So in the last slide, I will just like to highlight the impact of this pre-equilibrium phase, which they mentioned earlier, is missing from these low energy calculations. Yes, usually at a REAK and a LSC, people used to ignore this pre-equilibrium phase rather than model considering the free streaming, because they assume the lifetime of this QGP phase may be very small. The lifetime of this pre-equilibrium phase is very small, it may not happen. But this pre-equilibrium phase, the energy density is very large, so this may affect the heavy quark dynamics. And the recent calculation to study the heavy quark dynamics in plasma, the strong gluon field indicate when this heavy quark propagating this free plasma phase, what happened? Due to the strong diffusion, this low momentum heavy quark shifted with the high PT, and it will compute the suppression. Then instead of nucleus, the array, then instead of a suppression, we will get an enhancement, as we can see, and this is consistent with the proton nucleus collision. And similarly, if someone will include a pre-equilibrium phase to study the QGP phase, to study the heavy quark dynamics in QCD matter, as we can see, initially we will have an enhancement. The initial condition will be different if we consider a free streaming. So this initial enhancement due to the diffusion dominated plasma phase can significantly alter the array V2 dynamics. And recently there are several other works in this direction also, but the most important observations is the heavy quark diffusion within the correlator method by this Lapie et al. And they observe the initial rapid rise in heavy quark momentum burdening in the non-equilibrium plasma phase. And recently also we observe a ballistic diffusions of the heavy quarks in this initial plasma phase, where the variance is increasing quadratically instead of a linear behavior. Although lifetime is very small, but this may alter. Yes, at a low colliding energy, this plasma picture may not work, but meantime there are also some development within the kinetic theory or theory based on scattering. And one of these recent work by this Texas group, maybe Das-Dong-Song will talk about this later in this session, they have computed the impact of the pre-equilibrium phase from different viewpoints. First, they consider an anisotropic QGP medium with anisotropic momentum distributions of the QGP medium. Then in another scenario, they consider particles having larger or smaller kinetic energy in comparison to the thermal pattern in QGP. In another scenario, they also consider particle having smaller or larger whole mass in the spectral function in comparison to the QGP temperature, and they observe this impact of this pre-equilibrium phase is about to 20 to 30%. Considering the fact that at a low colliding energy, the lifetime of this pre-equilibrium phase might be larger, and this pre-equilibrium phase along with the hadronic phase may play a crucial role, and this will open up new window to study the QCD matter at finite baryonic chemical potential. And here is my conclusions. Here I would like to mention this open heavy flavor will act an excellent probe of high mu B matter, because it will open up new window to explore the QCD matter, which usually we ignore at a RIC and LSC energy. And this will also provide us a unique opportunity to characterize the hadronic phase, because the QGP phase lifetime will be small in low colliding energy. So this hadronic phase will play dominant role, and this V2 splitting between the DS and D and DS measure can help to characterize this hadronic phase, as well as this array and V2 dynamics may play important role to understand this QCD matter at high baryonic density. Also, at a low colliding energy, the pre-equilibrium phase may also play a significant role. And the array puzzle, as we discussed at a 62.4 GB, this already giving us some hint what lie ahead. So of course, due to lack of experimental data at a low colliding energy, it is yet to trigger any significant phenomenological interest, but still some works are there, and we certainly need more precise data and a new observable. Thank you very much for your kind attention.
We have time for some questions and discussion.
Can I ask a question?
Sure, please.
Can you repeat again the argument for harder RAA with Glasma?
Sorry, you are talking about this slide?
Yeah. Can you repeat again the argument for this harder RAA?
Oh,
Here.
this array in okay. So if we will consider a equilibrium phase and say we will model it in terms of a Glasma phase consisting of strong gluon field, when this heavy quark propagate in this Glasma, what happened? They trigger a strong diffusions, and due to this diffusion, it's mainly due to this diffusion dominated process, and due to this diffusion, what happened? This low momentum charm quark will shift to the high momentum. So if someone will take a ratio instead of a suppression, here we get an enhancement, and which is in fact consistent with what we observe in experiment in P-lead collisions. So here also, if someone will include this Glasma phase as a pre-equilibrium phase in lead-lead collisions, then what happens if we say consider in the pre-equilibrium phase as a free streaming? Then there is no change. If you take a ratio between the initial and final, it will be 1. This green dotted line. But if we will consider a Glasma phase as the pre-equilibrium phase, due to the strong diffusion in the Glasma phase, there will be enhancement, the red curve as we can see initially at say 0.3. Then one is at the red, another is the green. So if we further evolve to study the same array and V2, then it can alter the array V2 dynamics, or in other words, it can develop more V2.
Okay, so
Thank you.
Can I continue my question? So
No,
we have both.
No,
sorry.
let Ralph have the next question.
Yeah, so thank you very much for the nice overview. Can you go back to the lambda C V2, especially the effect of the hadronic phase seemed to be rather small compared to this one. I mean, lambda C has may have larger cross section than the D meson. Can you just comment on that?
Yes. So this is, of course, as I have shown in this comparison, as we can see, yes, this slide. Yes, the large lambda C and D meson, they have almost the similar drag coefficients, as we can see here, the similar drag coefficient. Then we have implemented this thing, and in this. So in this model we have implemented, but as I mentioned, in this calculation we have considered 156 as the quark hadron transition temperatures. So that reduces the lifetime of the hadronic phase, and maybe due to this, the contribution is about 20%. Say if we will not do this at a 156, we will include 165 or 170 MeV as the quark hadron transition. This gives a prolongated hadronic phase, and there the contribution might be more. And in this regard, I would like to remind the sensitivity of this quark hadron transition temperature on array and V2 we observe. This really affects significantly. And in this regard, I will cite this paper, how this quark hadron decoupling temperature really affect the V2 dynamics. I think this is playing a role instead of the interactions, the lifetime.
More questions. Francesco.
Yeah, hello. Now, this is a small comment on the comparison of data to models at the energy of 62 GeV at the week, because these are measurements with electrons, and you pointed out that there could be, let's say, phase space to improve the modeling. One thing is also that we know from measurements at the LHC and the top weak energy that the relative abundances of baryons and mesons and of d sub s with respect to D are different with respect to PP, or maybe different with respect to PP. And since the branching ratios to electrons are different for example, lambda C with respect to the meson, this is also something that should be included in the model. Namely, the one thing to check is that the model has the proper mix of hadronic state before decaying into electrons.
Sure. Thank you. Thank you for the comment.
Okay, thank you. You had a question?
On the same slide, I was wondering, what do you call it, this energy pre-equilibrium? And if you have any conceptual argument why it should play a role at this energy, apart from the fact that you, from this data model comparison that you made.
So you are asking why the pre-equilibrium phase will play a role here, is it?
Yes.
Yes, because I think in this low colliding energy, the lifetime of this pre-equilibrium phase will be quite sizable. And as mentioned, they are not including pre-equilibrium phase. Probably they have modeled this within the free streaming. And if this free streaming will replace with this pre-equilibrium interaction, then this may alter the dynamics. Maybe yes,
Do you
put some comment more in their calculation. Yes, sure, please.
How long is this free streaming, if you say that this is what is in the models?
So in this calculation, what is exactly, I cannot tell, but in RIC and LAC, usually in LAC, people consider say 0.3. And for a RIC, 0.6. Of course, different model use different thermalization time. They get this from the hydro. And in this calculation, I don't know exactly the time they are starting these QGP evolutions. But yes, it will certainly, if not one for me, close to 0.5 or something. Yes, the authors are here. Maybe they can tell more.
From the experimental point of view, if now we want really to go to low energy. So what I understand is that the RAA is less promising. What is more promising is, let's say, a study of the V2. It is more sensitive to what is happening in the hadronic phase. So let's say, this is a variable that is more statistics hungry to be studied, and let's say it develops at PT which are not too low. So I was wondering, should one be able just to have, let's say, a PT integrated V2, if this might be enough to catch a signal overall?
Yes, the PT integrated may help also, but here I will also like to mention, yes, this V2 is more complex as it used to be in the RIC and LSC, and over the years, several improvement has been done, and now we understand at least something quite decent. And yes, but here if we look at low colliding energy, yes, it seems we also need to understand the RAA as well. I think both these observable and simultaneous descriptions of this, all these observable along with PT integrated may help to understand the matter better.
Okay, thank you. Let's thank Santosh again. And we'll switch to the next talk by Jin-Dong, which is an experimental overview. Jin-Dong, could you please, yeah, thank you for switching on your camera, and please share your screen.
Thank you. And I hope this is visible to audience, and it is in full screen.
Yeah, thank you.
Thank you. And so first of all, I would like to thank the organizers for the nice invitation, and I apologize for not being able to be in Trento in person this time. And actually, I'm very looking forward to in-person discussions in the near future, if possible. So today I'll be try to give a review of experimental results on open heavy flavor production. And so the outline of my talk is I will give some brief introduction on my point of view, the goals using heavy quarks to characterize the SQGP properties. And I will review the recent heavy flavor results at RIC and LHC, focusing on three categories: IA suppressing, looking for the parton energy loss, and the heavy flavor hadron hadrochemistry to study hadronization, and the collectivity to this is a very sensitive measurement to really characterize QGP transport coefficient. So this review is mostly more selected results, focus on really study the hot medium, while I'll probably didn't mention the initial and the cold liquid matter effect in this talk. And then I would near the end talk about the future heavy flavor program at RIC and HC. And then I will discuss a little bit the heavy flavor production in the high MUB region. That's probably more related to this workshop. So I think we all agree that we are in the era of precise characterization of QGP emergent properties. And we know from the light flavor measurements that the low PT region is more very nice describe the hydrodynamics, and this suggests a very strongly coupled medium. And we often use AWS to characterize the QGP transport parameter, while at high PT region, and using the jet probes, and one can also show that the perturbed QCD calculation also works quite nicely. And this suggests also in this region, it's more like a weakly coupled region for the QGP. So the real question is really, how do we connect these two from a no to high PT region? And also in the no PT region, even here, what is the microscopic picture of this perfect liquid we are looking at? So the heavy flavor quarks really of a unique role here because of this large mass scale. I think I heard from the Santosh talk already. And in the large mass limit, when this mass is much larger in the temperature of the QGP, or the even also the interaction between the heavy quark and the medium, one can really characterize this transport of heavy quarks in the medium through this so-called Brownian motion, and using this Langevin stochastic equation to describe the kinetic equation. And I think one of the momentum motion here is described by a drag and diffusion in the medium. And I think the most interesting here, I think, is kind of connection to the QGP medium properties. We all heard already this heavy quark diffusion coefficient, and which describe basically the momentum space, spatial fluctuations per unit length. And this really have, I mean, from theoretical point of view, have a very nice connection in the no momentum region, that the relation between the diffusion, heavy quark diffusion with the AWS can really reveal the strong or weak coupling nature of the QGP, while in the high PT region and the spatial diffusion also have the momentum space diffusion also have a relation with respect to this Q hat parameter. So the heavy quark transport really in the medium can give us a unique tool to probe the QGP with very comprehensive PT coverage, and then offer unique insights to both a perturbative and non-perturbative region of in this during the QGP evolution. So the diffusion coefficient in terms of progress, we know that this is the figure or the status of the outstanding of the diffusion coefficient as of like 5-6 years ago, when we prepared this hot QCD white paper. And at that time, we know, I mean, there's not much precision there. That the constraint is that you can see the diffusion coefficient for the heavy quarks in the QGP medium. They really span a wide range, even up to roughly 13 TC. To determine this, and we really need a more precision data from the heavy flavor hadron measurement. I think the first is certainly the inclusive IA and V2, the commonly used variables, and particularly into the low PT region to really constrain this diffusion coefficient. So experimentally, to measure this heavy flavor hadron, and because their lifetime is so short, on the order of tens of microns to a couple hundred microns, and in heavy-ion collisions, the big challenge is this computational background from the primary collision. So one really need a very high precision silicon vertex detector, detector to separate this second vertex case from the primary collisions. So I'll quickly show you the current or in the past the detector, silicon detector from various experiments at RIC and HC. And I'll just point out basically the STAR experiment using the pixel detector based on the monolithic accurate pixel technology called MAPS. This really the pixel is a first application of maps in the collider experiments, and it offers very fine pitch size and very thin detector material. And this gives us a very high pointing resolutions particularly into the low momentum region, which we are most interested in. So this map sensors, now the next generation map sensor has been deployed for the ELISA ITS2 and also as Phoenix MVTX upgrades. I'll mention a bit in the end. And also they're being planned for the CBN and the DIC tracker as well. So then I'll move on to the review of the heavy flavor results. I'll first talk about IA suppression to look for the parton energy loss. This really started probably, go back into history 15 years ago when Rick first used the electron channel. The Phoenix experiment looked at the electron IA versus the momentum. In the radiative energy loss scenario, one would expect that this heavy flavor quarks will lose much less energy compared to the light quarks. So the IA of the, say, heavy flavor electrons will be smaller. However, the findings from experiments show the suppression is at a similar level at the light hadrons at high PT. This reveals basically the importance of the collision energy loss later on. And there's various models developed. However, as we just heard the comments in a few minutes ago, that the electrons really, to interpret this data and also have a precise determination of the QGP property, this got complicated because they have mixed contributions from various heavy flavor hadrons. So the experimental side, all experiments moving towards the precision measurement of the heavy flavor hadron through the hadronic decay channel. In the meantime, I think still in the QCD, in terms of energy loss, I still predict there's a very, I say still obvious mass hierarchy of this of different flavors, even including the collision energy loss scenarios. But another complication is basically those are at the parton level. When go to the experimental measurement, the hadron IA pattern will be a little bit complicated by like initial spectrum or the fragmentation, etc. So one will probably need to involve more theoretical calculation to have a more detailed understanding. So here I just put the latest measurements of the D meson IA from the RIC on the left side and LHC, the CMS data and ALICE data in central high volume collisions. And you can see the suppression level of the D0 at high PT is also similar as compared to the light hadrons, this other open symbol show light hadrons. Similarly, at LHC energy, you can see the similarity actually proceeds over a very broad momentum range. And this suggests certainly there's very significant charm quark energy loss in the QGP medium, very precise now. However, as I just mentioned a moment ago, here there doesn't seem to be an apparent mass hierarchy based on the D meson IA data. While actually later on from more sophisticated analysis from their side, this is not too surprising when you consider the initial spectrum and also a harder fragmentation for the charm at D0 mesons. So that currently, I think the more directions we are considering is really since the data now cover a very broad momentum range down to like nearly as zero, as low as 0 PT to high PT. This the D0 data really offers a unique tool to really dial in to study the relative contribution between collision energy loss and radiative energy loss and how they transition from low PT to high PT. So the charm hadrons seem to be at the IA level values seem to be similar as light hadrons. If you go further into the bottom sector, and that seems to be a very nice, not so nice findings. On the left, this shows the IA of the night hadron and D meson shown before, and in the meantime, we have the B hadron suppression, but tagged with either the lumprom D0 and also lumprom J psi shown on these symbols. You can see there's the suppression level is higher than the D0 at least the low PT below 10 GeV, while at high PT region they all converge also similarly. At RHIC energy, the statistics are quite challenging so far. Both STAR and Phoenix also measure the electron channel, looking at the bottom and charm decay electrons through the also vertex detector. And here I show the recent STAR data points that that suggest also there's a quite small suppression for the bottom decay electrons, shown as black symbol compared to red symbols. So you can see from bottom this tag channel that indicate this already show evidence of the mass hierarchy on the fast value of the particle energy loss. So those data now certainly need more precise measurement into the future. I'll come back to this later. So if we going down to intermediate PT region, where I think we believe the hadronization plays a quite important role, and this by looking at the say heavy flavor hadron hydrochemistry, we really can look into the hadronization mechanism. And taking a look at the baseline from the E plus, E minus, or EP collisions, we know from the this data, the fragmentation baseline for the charm hadron, this is harder than light, and the relative fraction between various charm hadrons, that's also quite well constrained from the E plus, E minus data. And this is based on the, say, fragmentation scenario. While this picture seems to be now challenged in heavy ion collisions by recent RHIC and LHC data by looking at the first, the DS, basically here is the charm strength meson to D0 meson ratio. And on the left, I show the DS over D0 ratio as a function of PT from STAR. On the right, this is a kind of a compilation of RHIC and LHC data from gold lead collision and compared to the PP collisions. Maybe let's look at the first right side, the PP data, and compared to the Pythia, this is based on the fragmentation baseline. They look very comparable. While heavy ion data, they show nearly a factor 2 enhancement at PT region, say below 8 or 10 GeV. And this is by comparing actually to various recent models where they incorporate the coalescence hadronization placed by recombining the charm quarks and also the thermalized strange quarks. While in the QGP medium, one expect a strength enhancement, this all reasonably qualitatively produced data, while the PT dependence seem to be still not well reproduced. So this is, I believe there will be more theoretical development to further look into this. In the meantime, as we also see, the charm baryons also become much more interest recent years. And by measuring the D lambda C baryon to D0 meson ratio, and the left plot show the STAR measurement. Also, the right plot show also a compilation of STAR and also LHC at least measurement. Sorry, I didn't put the CMS data point because that's a little bit high PT. But let's focus on this, and you can see this solid line is a Pythia fragmentation baseline. And while the data points certainly clearly in the heavy ion collisions were quite above this this baseline, and suggest also recent using the recombination of charm quarks and the QGP light quarks from QGP medium can qualitatively reproduce this enhancement. While in the meantime, one can also see the recent data point from at least the PP data point. This already show a very large difference compared to the PP baseline. So this actually attracts a very nice attention what's going on. And so in Pythia, one recent development is trying to incorporate the color reconnection with baryon junction mode. And one can see this actually qualitatively also reproduce the PP data from the LHC. And however, actually there are more stories, particularly recent development. I'll come back to in the next slide. But first, looking at the go data, if we put all this together, the relative fraction between the various charm hadrons to D0, this shows the D plus over D0, D sub S over D0, and lambda C over D0. And the solid line is the Pythia fragmentation baseline, while you can see that's data points are quite above. While now, in the meantime, which I show here, this is the thermal model calculation using the chemical Frieza parameter from the fit to light strange hadron. That shown currently, I think, a reasonable agreement with the data. So by combining all this, we can check the total cross section, and by combining all these major ground states, and the total cross section compared to the PP measurement, they now actually show nice unbalanced scaling from PP to AA collisions. However, we can see now the charm hydrochemistry changed considerably in go-go collisions. So come back to this charm baryons in the PP collisions, and the risk, quite several nice risk measurement from at least at the top plot I showed before the data points, the PP data from lambda C over D0, they are already considerably larger in the PP fragmentation baseline, while incorporating this so-called coronary collection with baryon junction, they're reasonably described data. However, this is not enough story, because the recent also studies measurement using the cascade C over D0. And even with this tuning, the Pythia model can still not reproduce the data. And while this is the other models, basically this is a kind of a coalescence approach similar to heavy ion collisions using tuned parameter. They more or less redescribe data, but I think so far there's still no coherent description of this charm baryons in the PP collision that will need certainly further attentions. On the right, this is fractions of various charm hadron to D0 ratio from PP collisions, and you can see the lambda C significantly above the default Pythia, although several tunings can reproduce lambda C, but the character C is still above all this model. So in the meantime, these measurements indicate that charm baryons can contribute also quite sizably to the total charm cross-section that really also need more investigation into the future. So moving also towards the bottom sector, so far this is also limited by the statistics in the data, but I'll show you this is the latest measurement from the B sub S meson over B plus meson measurement from CMS. And the LED data points show this red data points. You can see the uncertainty is still large, but they can kind of show a hint of enhancement compared to PP. And this is actually qualitatively also reproduced by this coalescence hydrogenation model calculations. Certainly the precision need to be further improved. And I want to also point out also in the LHC, we look in the PP collisions, looking at the lambda B over the light B meson fraction, and the lambda B over B meson also show already also increased trend towards low PT. You can see this is a very similar feature as a lambda B, lambda C over D mesons. So I think the bottom sectors will certainly be a very focused area into the future. So last experimental part I want to talk about is the collectivity measurement. This is one central focus is try to really constrain the SHB transport parameter, which this is a heavy quark special diffusion coefficient. I want to first, before going to the V2, first point out the radio flow. This is often not looked at very extensively. And but somehow we have precision data points cover even down to 0 PT region. And if you perform a simple, this is a probably experimentalist simple approach, just doing the Blast-Web model fit, extract the Frieza parameters function, the velocity, the collectivity beta value, you can see this D0 hadrons. They are quite different from the light hadrons, while they are actually comparable to the this multi-string hadron field results. And well, that suggests basically this D0 mesons really they see freeze out much earlier than the light hadrons, and so the collectivity is mostly from the platonic stage from these interactions. And so V2 is more kind of attractive, observable, and currently we have all very precision measurement from both RIC and LHC. And here I show the V2 scaled with number of constant quarks, plotted as function of kinetic energy, also scaled for NQ from RIC. On the right is LHC. Compared to all various light hadrons, first, certainly the V2 of the D0 is very significant, while you can see also with now the precision data, the D0 V2 now seem to be very nicely follow this scaling as light hadrons. This suggests also the charm quarks may already achieve the local thermal equilibrium in the QGP medium. By comparing so what does this large V2 come from? A simple test is looking at compare the D0 V2 with say this model or Tamu model by turning on or turning off the charm quark diffusion. One can see certainly that the majority, the diffusion is a very critical component to reproduce a large V2, but certainly one can argue that this is also coupled together with a medium evolution. So in the meantime, you can see also there's a very latest 3D viscous hadron calculation. There should also nice agreement with the D0 V2 up to 4 GeV, but this is also probably can be predictable based on the scaling shown before in the previous slide. So coming back to comparing the diffusion coefficient, and we can compare to basically a few of the early calculation, first like the perturb QCD, and they really show this is for the perturb QCD, the V2 is just too small to be able to reproduce data. So this is certainly not a good scenario to by using the data constraint. And another comparison we can see in this T-matrix approach, there's an option to using the free energy potential or internal energy potential. Well, free energy theory called weak, and part you can see by comparing the LHC data points, this scenario also is too far off from the data points. So we can now, by comparing using this precision V2 data, we can exclude all this scenario now. And I want to also just emphasize this heavy quark free energy potential scenario also disfavored by the heavy quarkonian RAA data as well. So let's just do a comparison and also from data and the model. And here on the left side, I summarized the D0 V2 and the RAA from RIC and LHC together. And on the right side, this is the calculations from various models for the LHC energy, just as an illustration. From data point, you can see there's a very distinct feature of both RAA and the V2 that show a rise and then going down and at high PT. And so this is all more reasonably now captured by the model or various model calculations now. So the data points now provide a quite good constraints and with the model to the models. And with this, we can now look into the diffusion coefficient, and you saw this figure before. And I put just a comparison, like 6 years ago, we see this the diffusion coefficient, and our understandings go over a very wide range. But now we can really go very nice constraint for all these models. They predict this diffusion coefficient is in the range of between roughly 2 to 10 or 12. So I would think this is a really very great achievement by a joint effort from the precision experiment data and also very latest sophisticated theoretical model calculations. So as I mentioned earlier, one nice motivation is to how do we connect this heavy quark diffusion coefficient with, say, the AWS in the medium. And this can provide our basically a microscopic picture of this strongly coupled perfect liquid. And on the right side, this is based only the Duke-Bayesian model calculation that extract the charm diffusion coefficient in comparison with this AWS. We know in the quantum limit, this values to reach about 1. And the shape of these two, you can see they're very similar, while the values are a little bit different. Currently, the uncertainty band is a bit too large, but I think it's a very good direction to, with more precise or more data in the future and or more sophisticated model calculations, we can reduce all these uncertainties, and this can reveal, help us to reveal the nature of the QGP medium. As I mentioned, I think one of the great achievement now is we now know the charm quark diffusion coefficient, particularly in the near TC region, in the order of 2 to 5, and the lattice calculations, you can see they show, although the uncertainty is large, but they show also reasonable agreement now in this range. So by, as I mentioned, then one of the next direction I was seeing is trying to look into temperature dependence of the diffusion coefficient. So one of the arguments I would say is using the this D0 direct flow V1 measurement. Because we know the V1 is developed much earlier in the through the collisions, and the recent also hetero calculations show this is the D0 V1 basically the V1 as a function of rapidity, this slope parameter has quite sensitivity to the temperature dependence diffusion coefficient. Here I show the predictions show using 2 different temperature dependence that show quite different predicted values. So there's already measurement from RIC and also LHC. Then here right side show that D0 V1 as function of rapidity. And you can see that D0 V1 show very large slope compared to the light mesons. And this is the K mesons. There's a finite slope, but just because the magnitude is too small to see in this scale. The model calc predictions show a large value, but still cannot reproduce data. So this is still need to be further developed. I'm looking forward to using this data to further constrain the diffusion coefficient, the temperature dependence of diffusion coefficient. The D0 V1 on the outside, I think there's one unique aspect is by looking at D0 and D0 V1 difference. This provide a unique access to the initial magnetic field because heavy quarks are produced more through mostly from the initial hot scattering. So the charm quarks can feel this initial strong magnetic field, and due to this Lorentz force, we would expect that D0 and D0 bar will show a opposite sign of this V1 due to this effect. While on top of this, there's also a hadron devolution to push this V1 out. So one would expect basically a large slope of the D0 and D0 V1, but also with a split between the D0 D0 bar. The experimental data that currently show in the RIC, actually shown left, the uncertainty is still too large to be conclusive at this moment, while actually at least data show instead there's a very significant difference between D0 and D0 bar V1. And the slope parameter is so significant on the order of nearly 0.5. And also the sign is different compared to the prediction. So I think this is really require more detailed investigation into the future, both from experimental side to improve the precision and also more theoretical development. So in the last few minutes, I will give some overview of the future heavy flavor program at RIC and HC, and also mention about the high mid B part. The experimental part, as I mentioned, both RIC and HC are utilizing this next generation fast match detector to further improve the heavy flavor measurement. One of the unique features of this detector is trying to reduce the integration time of the from HFT from like around 200 microseconds down to below 10 microseconds. This will consider reduce the background in the high luminosity RIC and LHC environment by more than factor 10. On the bottom right, I show the quick the feature. This is probably a little bit technical, but very crucial from experimental point of view. And this show the so-called the DCA, basically the pointing direction from the HFT data. You can see a very narrow peak, basically from the signal evaluation, but while in the HFT data, there's also large background because of this the long integration time. So the much shorter integration time will reduce all this background considerably, so one can really push down to low PT with high precision. So the RIC and LHC program now is looking for more precision heavy flavor measurement. I think the flagship outing is looking for the precision bottom sector, because this is give us a dial to look into this mass hierarchy of the particle energy loss, and in the meantime to looking for the bottom quark diffusion coefficient. Since the bottom quark mass is much heavier than the charm, and this from theoretical side, this longevity approach should work much better for the bottom. So to check this charm bottom universality is also one very important task in the future. So with this detector here, show the projection of the IA and V2 from the S-Phoenix, and in the low PT side using the display D0 tagging, and also in high PT in the BTAC jet. What I want to emphasize, the point is basically with this detector, one can really have very broad momentum coverage from down to as low as 0 PT down up to in the RIC energy, basically to the kinematic limit for both IA and V2 measurements. I would say similarly at LHC, and here I showed a projection from ALICE and the IA of D0 and the long prompt D0, basically from bottom decays, and also V2 from both long prompt D0 and long prompt JSI. CMS has also upgraded, although to improve the pixel detect capability, and that also can considerably improve the charm and bottom measurement as well. So, I think in the near future, from both RIC and HC, we're really looking to also a precision measurement of focusing on the bottom side, although they certainly will provide much better precision on the charm as well, but to look at the IA, V2, and the hydrochemistry. So this precision data will not just allow us to look at the IA and V2, but also more other differential measurement or charm or various other charm hadron states, because as we just heard, the hadronization is still very not well understood or well constrained at this moment. So by looking at the charm, particularly like a charm baron lambda C in PP and AA collisions through precise PT dependent and central dependent measurement, this will give us more insight into the heavy quark hadronization in both the PP collisions and also in the QDP medium. And as I mentioned, just near the end, D0 and D0 bar V1, this really have a unique access to both the temperature dependence diffusion coefficient, as well as to the initial magnetic field. And more precise data now really can give us a more decisive answers to see whether this is just a projection show the sensitivity, and whether this features an initial field can be seen from this D0 measurement. So I'll spend the last couple of minutes.
You have 3 more minutes.
Thank you. Yeah, perfect. To talk about the heavy flavor production at high mu-B region, and certainly going down to low energies, one would think something that down into the temperature dependence of the diffusion coefficient. But in my view, and one would also can have another axis looking at the mu-B dependence of the diffusion coefficient, similar as a QGP transport parameter. So we heard already in the last talk some discussion on this low energy electron V2 measurement, and that here Here I show some recent measurement from STAR, looking at the 54 GeV and 27 GeV hyperstatistical measurement down to a relatively low PT region. One can see actually 54 GeV that the V2 is comparable to the 200 GeV, while 27 GeV there's a hint of a small a low value. However, still the precision is not enough. One interesting feature is one we can look at the energy dependence of this various hadrons, and this is to show V2 at the fixed momentum region. And for electrons, we use the fixed the corresponding d meson kinetic PT region. And you can see certainly at high energy RIC and LHC, this all show nice agreement, as we see already from this nice NCQ scaling from D0 meson measurement. While when you go to low energy region, they seem to indicate there's some hierarchy, this mass effect start to show. However, the data point is still not precise enough. Really, we want to have better measurement, definitely, to constrain this mu-dV dependence diffusion coefficient. I think we also heard about when you go to further along to low PT, another interesting feature also to look using the charm quark transport to look at also this medium properties. This is a calculation shown at basically as cis 300 energy region, but could be suitable for various other facilities as well, showing the IAA, the predictions with respect to PCA baseline and the V2. And there's two distinct features. One is IA that show actually very sharp increase towards the this kinematic region. This is introduced by due to this charm and or D meson diffusion in the medium, basically boost the charm or D meson to the little bit high PT, while this region already reached the kinematic minute in the PP collision. So that gives you a very sharp increase. In the meantime, we can see also the models predicts very also sizable V2 due to the diffusion of the charm and D meson also in the medium. And also there's a difference between the C and C bar, certainly due to the baryon mu B, finite mu B. Another interesting feature is looking into the hadron relation of various charm hadrons, and the statistical model predict basically due to the higher band density region, the charm baryons will be significantly enhanced, and also there's a different split between the D and the D0. And I think we'll hear more from Anton's talk later. And this is certainly can be checked as well when we go to low energies. In the meantime, this high density region, they also various QCD models that predict this high density will have a modification to the charm spectral function, will lead to either a mass shift or the broadening of the D spectral function. But the various model predicts quite different change in the mass positions. And the change of the mass position will need to also if in the statistical hadronization scheme, the composition between different charm hadron will be different as well. So this is actually very nice and new feature, new territory that can be further explored when we move into the low energies. So I'll summarize my talk. I think over the last few years with more precision data and also sophisticated the state-of-art theoretical models, one can now make a very nice achievement by constraining the charm quark diffusion coefficient in the region between at the RIC and LHC energy, and the values probably around to 2 to 5 near TC region. In the near future, I think our goal is trying to, at least from the experimental side, to looking for more precision measurement to constrain the temperature dependence, and also looking to the bottom sector, this QGP transparameter. And I'm looking forward to on the experimental side, also the similar development, and also how to relate this to the other QGP transport parameters, so we can provide more microspec picture, really how this QGP is formed. Future, I believe there's also very nice program planned from FAIR, NICA, SBS. I think there are no more detailed more talks later today to talk about all this. I think two important aspects is really look into first the transport in high B, the charm quark and D meson in the high B region, and also look into the how the heavy quark can be used to heavy mesons can be used to determine to the higher baryon density region. So I will stop here and thank you for attention.
Thank you, Chin. Thank you for this comprehensive overview. We have time for a few questions. Enrico.
So indeed, thanks. It was very interesting as a review. With an eye to the, let's say, high MUBI region, the values for the ds over d, for the lambda c over d, it might seem that they are even more increasing when going from LHC to RIC towards lower energy. This might be not completely significant from the statistical point of view. I was wondering if you have ideas if these effects on the ionization might become even more important once one gets to, let's say, SPS energy, for example.
I think absolutely. I think so when you go to low energies, I think there are several aspects might change. Basically, the first, this enhancement in the ds over d0 or lambda c over d0 seeing the Evian collision, the RIC and HC. We attribute this to the QGP in QGP medium features by recombine the D meson charm quarks with the light or strange quarks in the medium, and we know that this for the DS meson side, this certainly require a strange enhancement to see this effect. So this the strange enhancement has a very strong certain energy dependence when moving down to the SPS energy. This certainly will be is a very nice feature to be checked out as well. But this also could be balanced because also the QGP or evolution SPS energy is different from RIC. So that kind of two effects could be also, I don't know, the direction maybe cancel or maybe boost towards one direction. So that certainly would be very interesting. Another thing also is certainly the MUBI, the high finite MUBI will introduce a difference between the particle and the antiparticle. Similarly for DS, and then finite µs also give you a difference between the DS, and DS bar. So DS plus and DS minus. So this would be, this is based on the statistical organization model predictions, right? And to give you the total yield. And in the meantime, the momentum dependence would be also quite interesting to looking at the more kind of a dynamic model calculating how that can reproduce the data. I totally agree. I think that's a very, very important direction.
Thank you.
Thank you.
One urgent question? Okay. Yeah, it's fine. We have time for one more question.
So I noticed your open charm cross sections that you put in some table there. And there was a value, I think we were so correctly, of like 120 or so, 130, 150. So that is not that far from the Phoenix values anymore, right? Which I remember also.
Phoenix is probably it's still smaller. It's probably 110.
Yeah, 120. So this is now within the arrow. So I think that's very good news, right? It seems that the charm cross section, which was quite different at the time in the past. So this seems to be very consistent now. I think that's great news, huh?
Yeah, it's I think within uncertainties, there's before there was only still also 2 sigma. I think it's considering all the experimental uncertainties, but although the central value indeed differs. Yeah, now it's getting closer as well. Yes.
Okay, let's thank Jin again for this nice talk.
Thank you.
And now we turn to Teizo Zhang. who's going to tell us about non-equilibrium effects on charm observables.
To the people from outside connecting to Zoom, please do not forget to mute yourself.
Hello, everyone. My name is Das-Dong-Song. I first thank organizers for giving me this opportunity. I will talk about traces of non-equilibrium effect in the charm observables and quaconia. And my collaborators are Pierre Moreau, Elena Brakovskaya, Yuk I. Klein, Stefan Bass, Paul Gosho, and Marle Nargang. This is outline of my talk. I will give you a short introduction and motivation, and explain about Paton-Hadron string dynamics, and then coarse graining and linear Boltzmann approach tried in Paton-Hadron string dynamics. And if time allows, I will briefly talk about quaconium production and dissociation planned in PHSD and summary. Heavy flavor is a good probe particle for a hot dense nuclear matter created in heavy-ion collisions. Firstly, it is early produced, so it probes the matter from the early stage of heavy-ion collisions. And the production of a heavy flavor needs a large energy momentum transfer. So QCD is applicable, and we are model independent and more advantages. In vacuum, heavy pair is produced by perturbative QCD, and this charm and anti-charm or bottom and anti-bottom hadronized to DD-bar or BB-bar through fragmentation. But if this process happens in heavy-ion collisions or in nuclear medium, we have changes in kinematics and in chemistry because of interaction with the nuclear matter. Charm and anti-charm change its momentum and energy, and also chemistry changes by the other method of hadronization, like coalescence. Let me show you one example. This is invariant mass spectrum of dilepton from DD-bar pairs. Firstly, CC-bar pair is produced, and this pair hadronizes to DD-bar, and then E plus E minus produced through weak decay. And there are two lines. Blue line is invariant mass spectrum without hot nuclear matter effect, and the red line is with hot nuclear matter effect. So QGP exists or not. And if collision energy is low, like SPS energy, that is left side, there is no difference between two scenarios. But in the right side, this is Rig energy, and we can see the difference. The hot nuclear matter suppresses invariant mass spectrum to lower at a large mass. This is just one example, and there are many examples. And how to describe nuclear matter? There are two representative methods. One is hydrodynamics, and the other is transport approach. And hydrodynamics is a macroscopic approach, which assumes a local thermal equilibrium, and it solves hydrodynamic equations, which is nothing but energy momentum conservation of fluid cells. And the equation of state is given by the relation between pressure and energy density. On the other hand, transport approach is a microscopic approach, and it does not assume local thermal equilibrium, and it solves Boltzmann equation or Cardan-Baum equation, and the energy momentum conservation of particles is taken into account, and the equation of state is given by the properties of quasi particles. And then how to describe heavy flavor in the nuclear matter? The simplest way is to solve a Langevin equation. Suppose we have a charm with a certain momentum, then its distribution is expressed as a delta function in longitudinal momentum and transverse momentum. And this delta function is located at the initial momentum in longitudinal momentum axis, and it is located at 0 in transverse momentum. But after scattering or interaction with the nuclear matter, this peak position is shifted to lower longitudinal momentum because of energy loss or strong interaction. And also this sharp distribution broadens because of random scattering. So this peak shift is called momentum drag, and this broadening is called longitudinal momentum diffusion. And this momentum diffusion happens also in transverse momentum. And this transport coefficients like drag and diffusion are pre-calculated as a function of temperature of the matter and the heavy quark momentum before carrying out simulations. The other way is to solve Boltzmann equation, and this Boltzmann equation can be separated into linearized Boltzmann equation and full Boltzmann equation. In linearized Boltzmann equation, coarse graining is introduced, and local thermal equilibrium is assumed. Let me talk about this linearized Boltzmann approach. In transport approach, the degree of freedom is particle. And first, we introduce a grid, which is shown by dotted lines. And then energy momentum tensor and the baryon current are calculated in each grid cell. And diagonalizing the energy momentum tensor, flow velocity and energy density, pressure, and baryon charge density in cell-less frame are obtained. And assuming local thermal equilibrium, local temperature, and the local baryon chemical potential are obtained from energy density and baryon charge density. So in this linearized Boltzmann approach, the left figure is converted to right figure. Yeah, now we have fluid cell locally summarized, and in comparing two figures, energy density and flow velocity and baryon charge are exactly the same, but the left side is in non-equilibrium and the right side in equilibrium. And we can make charm heavy quark interaction in both cases, and we find some differences between them. Then that is non-equilibrium, the effect of non-equilibrium matter on heavy flavor. Let me briefly talk about Parton-Hadron string dynamics. Parton-Hadron string dynamics is based on a dynamical quasi-particle model for quark-gluon plasma phase. In this model, quarks and gluons have a spectral distribution with pole mass and the spectral width, which depend on temperature and baryon chemical potential. The mass and width are given by hard-sum law calculations at high temperature limit. But these hard-sum law calculations are not valid near TC. So we use sophisticated strong coupling, which depend on temperature and baryon chemical potential. This is our strong coupling, which depends on entropy density divided by entropy density in Stefan-Boltzmann limit. And we introduce three constant parameters like the D, E, F for some purpose. And then this strong coupling is extended to non-zero baryon chemical potential by using this this relation. Strong coupling at non-zero chemical potential equals strong coupling G squared at zero chemical potential with rescaled temperature T star divided by Tc, and this T star has additional term here, quark chemical potential square divided by pi square. So this is this T effective temperature is always larger than normal temperature at finite baryon chemical potential, and Tc has additional factor square root 1 minus alpha mu b square, and this mu alpha is positive. So this Tc decreases with increasing baryon chemical potential. So effectively, this ratio is a larger increase at large finite baryon chemical potential because T star increases and Tc decreases. So this temperature ratio increases. So our strong coupling at a finite baryon chemical potential decreases. That is this figure. Strong coupling alpha s as a function of temperature for different mu b, and we can see the decrease of strong coupling with increasing baryon chemical potential. And from this parameterization, we obtain quark pole mass and quark width and gluon pole mass and gluon spectral width, and we can reproduce lattice equation of state both at zero chemical potential and finite baryon chemical potential. And then we make scattering with this quasi-particle, with the charm scattering with the quasi-particle. And then we calculate this scattering cross-section, and then we can reproduce lattice data on spatial diffusion coefficients. And then let me move back to coarse graining and the linear Boltzmann approach tried in PHSD. We used two different coarse grainings. In the first case, we used constant dg, and the other case, we used constant d eta, spatial pseudo rapidity. Nuclear metal expand in heavy ion collisions, so our the cell size increases with the time, but this dg is always constant in each time step. But in this case, the cell size depends on where the cell is. If cell is located in mid rapidity, the size is large, but if it is located at forward or backward rapidity, then cell size is small. So the resolution is good at mid rapidity in the former case, but in the latter case, constant d eta, the resolution is good in forward and backward rapidities. And we used these two different coarse grainings. This is real situations. Particles are less populated in mid-rapidity and more populated in forward rapidity because of Lorentz contraction. But if we use constant dz, we just ignore this difference of populations, just take the same size of cells and calculate temperature and varying chemical potential. But if we use this constant eta grid, then our cell size changes is large in mid-rapidity and small in forward rapidity. And this is original pH calculations. We don't assume local thermal equilibrium. Interactions is always with particles, not a fluid cell. And what happens if we try heavy core interactions in these three situations? This is charm distribution, rapidity distribution at TC. Collision energy is 200 GeV and impact parameter 2 Fermi. And if you look at mid-rapidity, there is no difference. In any case, the results are same. But we found some strange shoulder structures in forward and backward rapidities. In the case of constant dg, and these are artifacts from the bad resolution at forward and backward rapidities. And this is effect on RAA at mid rapidity. The left side is RAA of charm at critical temperature, and we can see little effect at low transverse momentum. In PHSD, RAA is a bit lower than linearized Boltzmann approach. But after hadronization and hadron scattering, this small difference disappears. And almost same, whether we use PHSD or linearized Boltzmann approach. And this is effect on electric flow. And we can see differences, but it is not so significant. So there seems no significant effect of a non-equilibrium matter. But what happens behind? Let me tell you about behind the story. This is transverse momentum drag and the diffusion. This y-axis is change of transverse momentum of a charm. A final transverse momentum minus initial transverse momentum as a function of initial charm momentum. And we can see the positive change at low transverse momentum because of flow. Flow pushes charm to higher transverse momentum. So this change is positive, but it becomes negative at large transverse momentum because of energy loss. But we can see the larger energy loss in case of PHSD compared to linearized Boltzmann approach. And we can see the similar differences in diffusion. This is variance of momentum change. And this variance is larger in PHSD. And this is PT distributions from each initial PT. I mean, this is PT spectrum of a charm, but this red line is PT spectrum of a charm whose initial momentum was 1 to 0 GeV. So it was initially located between 0 and 2, but after interaction with the nuclear matter, it spread to larger transverse momentum. And this blue line is the charm distribution, the distribution, PT distribution of a charm, whose initial momentum was 2 to 5 GeV. But now it moves to lower transverse momentum and higher transverse momentum. But the peak position is a bit shifted to lower transverse momentum. And we can see the same for 5 to 8 GeV. And the black line is some of them. Comparing this PHSD analysis and linearized Boltzmann approach, we can see the differences. This red line and this red line and this blue line and green line. But if we sum all of them, then the differences disappear. So there seems to be compensation between larger momentum drag and the larger momentum diffusion in PHSD. So we cannot see the difference in overall results. And one possible reason for this non-equilibrium effect is following. Yeah, this is PT spectra of partons scattered by charm. So this is not charm spectrum, but parton spectrum scattered by charm in heavy ion collisions. And you can see the parton spectrum, the PT spectrum of parton is harder in PHSD. So it can be the reason for larger transfer, larger momentum drag and larger momentum diffusion. But there are hidden and more complicated stories. We studied the origin of non-equilibrium effect, and there could be a non-equilibrium in momentum anisotropy and kinetic non-equilibrium in kinetic energy and the non-equilibrium in quasi-particle mass and so on. So anyhow, a non-equilibrium effect will be more important at lower collision energies or higher MUV because it's harder to reach thermal equilibrium. Let me briefly talk about quaternion production and dissociation planned in PHSD. Yeah, this is the trajectories of heavy quark and heavy anti-quark, and it's not straight line because of interactions. And how to use this information to study quaternion. First, each time step we calculate Wigner function for scattered heavy quark and heavy quark with all existing anti-heavy quark, and for scattered anti-quark with all existing heavy quark before scattering and after scattering. And the Wigner function before scattering is subtracted like this, and the Wigner function after scattering is added, like the first term. And this is kind of a regeneration, and this is kind of a dissociation. And we calculate these Wigner functions in each time step and accumulate that, and then that is the production of quaternion in our model. And considering the energy loss of heavy flavor, we expect this Wigner function will be enhanced at low transverse momentum and suppressed at a high transverse momentum. And we tested this method by using PP collisions. In this case, there is no regeneration, only and there is no dissociation, only production. So we take into account only the first term, and we make use of this initial the charm spectrum and charm lattice distribution, and calculated the charm production in PP collisions and compared the experimental data at rig and LHC energy, and comparison is not bad. And also we calculated feed down ratio from chi-sin psi prime to j psi, and it is also within experimental error bar. So this method looks promising, and we plan to extend this method to heavy ion collisions. And this is my summary. We have studied non-equilibrium effect on charm by comparing original PHSD and the linearized Boltzmann approach, and assuming local thermal equilibrium, in linearized Boltzmann approach, momentum drag and the diffusion a bit smaller. However, at middle PT, final spectra are similar because of the compensation between less drag and less diffusion of charm in the linearized Boltzmann approach, and this effect will be more important at lower collision energies, higher μb, and quaternion production dissociation looks by using the Wigner density function looks promising. Yeah, thank you.
Thank you. Okay, we have again time for a few questions.
Yeah, no, this is a curiosity on the quaternion or the QQ bar transport that you have shown at the end. So in the case, just for my understanding, in the case of lead-lead collision, your plan is that you will transport at the same time all the 100 pairs that you produce, for example, in a LHC collision through the same, let's say, underlying medium, and you compute the Wigner function for each pair.
Yeah, each time step.
At each time step.
And all possible pairs.
And all possible pairs.
Yes.
Okay.
But if the distance is large enough, then we can ignore that pair.
Okay. Any further questions? That does not seem to be the case. So let's thank Tezo again. Thank you. The next talk will be by Francesco Pino, and he will tell us about the opportunities with NA60 plus.
I start my talk by thanking the organizers for giving me the opportunity to come here and to tell you something about the perspectives that we have for measuring open charm and also strange hadrons with the future NA60 plus experiment at the CERN SPS. So there was a very detailed talk on Monday by Alessandro on the NA60 plus project, so I will just flash the main points that will be useful then to discuss open charm. So it's an experiment that we are proposing for the next years at the CERN SPS, and essentially profiting of the high interaction rate that could be achieved at the SPS in fixed target mode to study where probes, so in the hard and in the electromagnetic sector, using a setup that allows to measure the muons in the muon spectrometer, but also to perform hadronic measurements using the Vertex telescope based on silicon. And this will be the main player of the presentation of today, which will be focused on open charm. And so the main goal is to study the QGP properties at high mu B by performing a beam energy scan in the root S range, which can be covered with SPS, so between 6 and 17 GeV of center of mass energy, taking, of course, that collision, but also for each energy the necessary reference for proton-nucleus collision, which more than being, other than being a crucial reference for AA collision, as I will show today, offers also some interesting opportunities of studying processes in proton-nucleus collision. And the high rate will allow to measure well probes in the dielectron sector and with hadronic measurements, and we will focus mostly today on the measurement of charm mesons and baryons. And the benchmark studies that were done for the expression of interest were based on the reconstruction of D0 mesons. And the goal is that for each energy of the beam energy scan, we may be able to have order of 10 to the 7 reconstructed D0s. So let me start by saying why we want to do all this. So what is the physics motivation for measuring open charm with NA60 plus? So here we have a shopping list. Many points were already touched by the previous speaker, and I will try to go a bit in details to highlight the specific feature of the measurement at low root S, and what we should keep in mind that as of now we don't have results or precise results available below the top SPS energy on open charm production. So let's start from PA, or if you want PP. So there are measurements of the meson production cross-section taken from this compilation at energies which, as you see, the scanned energy is from, let's say, the top SPS energy in the case of nuclear collisions above, and a measurement essentially of D0 and D plus. And from this measurement of D0 and D plus, there was an estimation of the total charm cross-section, which however, is, let's say, affected by the fact that one had to assume the fragmentation fraction from E plus E minus, and this was already discussed in the previous talks, might not be the good case in the case of hadronic collisions. And what we see here, and this will be important then to support our estimates, is that the root S dependence of the cross sections is reasonably well described by pizza simulation using only leading order processes and then scale them with an appropriate K factor, which is essentially fit to the data. And what we see is that when we go at the root S of AA collision, lead collision at the SPS, we go below 10 microns of chunk cross section. And here are some more modern plots maybe, which show also the chunk cross section measurements at week, not updated with the last number shown by Kindle in the talk before, and at the LHC. And we see that the root S trend is catched also by PQCD calculation at next to leading order, next to leading log, and next to leading order, which starts to be available. And you see that the uncertainty shrinks when we have the new calculation at next to leading order. And one other important point is that the new measurements from Alice at the LHC include the lambda C and the Xi C baryons, which, let's say, come with an increase of the estimated cross section by about 20% as compared to the extrapolation that was done before using only the D mesons. Now, of course, we will measure PA collisions, and this will allow also to study the nuclear PDFs at SPS energies, and this will allow to probe the region of Bjorkenx where EMC effect and anti-shadowing are dominant with our, let's say, energy range. As you see here, this is the expected RP-LED based on EPS09 parameterization of the nuclear PDF. And as you see, we could get precise measurement in a region where the uncertainty on the nuclear PDF is large, so we could contribute to better characterize the nuclear PDF, also studying their dependence on the A numbers, on the number of nucleons in the nucleus. And another point that I touch, which we should work on to see if we have a possibility to provide important measurements, is that of intrinsic charm. This is let's say a strong or rigorous prediction of QCD, the existence of a non-perturbative intrinsic charm component in the PDF of the proton. And based on the calculations that were done for the after experiment at the LHC, this component should manifest as a large enhancement of charm production cross-section at large rapidity and large PT, because this is an effect of large Bjorkenx, and we are in contact with experts in order to have calculations also for our use case to see if we have room to make important measurement in this sector. Now let's move to AA collision, which is what we are mostly focused on in this workshop. So I think it was already touched by the previous speaker, the fact that the measurements of open charm could provide important constraints to the transport properties, and in particular this diffusion coefficient, and now we all know very well what it is and what is important for. And in particular, measurement at SPS energies could provide an important view on this for the question of the possible dependence of mu B, but also on the fact that the relative balance between the QGP phase and the hadronic phase would be different with respect to what we have at WIC and at LHC. And so it could provide constraints, as we have seen also in the talk by Santosh before, on the transport in the hadronic phase, which would be complementary to the studies that are being done to estimate this diffusion coefficient using the LHC and the WIC data. And also elliptic flow, of course, a measurement at low energy for the mesons would be useful. As you have seen before in the summary of the experimental result, there exists measurement of V2 at the energies of the beam energy scan by week. They were done by Star and Phoenix using heavy flavor decay electrons. However, as you see, the uncertainties, the current uncertainties are large. They show that V2 is smaller than the one at top SPS energy. However, they are not conclusive on a possible finite V2 or a zero V2. And so having precise measurements at SPS energies for this would be, of course, crucial to study the thermalization or the hydrodynamization of charm quarks in a short-lived QGP. And then, okay, a lesson that we learned at the higher energies, and that was also mentioned before in when commenting on the previous speaker, is that having a view of the hadrochemistry, so the relative production of different hadron species, is crucial. First of all, to get insight into the hadronization mechanism, because it's standard prediction of models which implement hadronization via coalescence, that we should expect an enhancement of the production of d sub s with respect to d0 due to the strangeness-rich environment of the QGP. And there are indications from the measurement at the LHC and at RIC that this is actually the case, and extending this measurement at lower root S would complement the studies of strangeness production and strangeness enhancement that were carried out by NA49 and now NA61 experiments. And also in the sector of the baryon over meson ratio, one expect that in the case of hadronization via coalescence, at least in some PT, intermediate PT region, there should be a significant enhancement of baryon production. This is what is suggested by the ALICE measurement. You see here in green the points of lambda C over D0 ratio from PP, and in red and blue those from lead, which show an enhancement. And here you see the same measurements at by Star at weak energies, and you see that the measured points are actually captured well by models that include component of hadronization via coalescence. And also this is crucial, a crucial measurement also in PA collisions, because a lesson that we learned at the LHC is that the production in PP and P-lead collision is substantially enhanced with respect to E plus E minus collision, which essentially is this Pizia baselane that you see here. And this is described either by models implementing coalescence, so let's say the hadronization mode that we think is relevant in the case of hadronization of a QGP. It's captured by statistical hadronization model using a set of excited charm baryon states. This is this green band, or it's described by Pizia using color reconnection. And having data at lower root S could indeed be useful to disentangle among these different possible explanations. And measuring all the different states is of course crucial then to extract the total charm cross-section, for which there exists an upper limit in lead-lead collision by Na49 based on D0 mesons, and in indium-indium by Na60, but you see there is a lot of room to have more precise measurements at SPS energy. And indeed at low energy there is a prediction that the charm cross-section could be sensitive to chiral symmetry restoration, because an enhancement of charm production is expected due to a reduction of the threshold for the production of a DD bar pair close to the chiral phase transition. So I think I mentioned several reasons for which it's useful to make the effort to measure these guys. And so now I will dedicate the second part of the talk to explain how we plan to do it. So the tool would be to reconstruct fully reconstruct charm mesons and baryons by using their decays into 2 or 3 charged hadrons. You see here the main ground state for mesons and baryons, their decay mode, which include kaon, pions, and protons. And what we see is that the branching ratios are smallish, and also, as I already mentioned, the production cross-section is small. This means that a measurement of these hadron species requires large samples of minimum bias collisions and come with a huge combinatorial background. So what one has to do is to exploit the relative large lifetime of the mesons and lambda C baryons, which result in mean proper decay length of the order of 100 microns or so. You see here what is for the different mesons. And this calls for having a high precision tracking and vertexing detector that allows to separate the charm hadron decay vertex from the interaction point. And therefore, in the NA60 plus setup, the main player for these measurements will be the vertex telescope tracker that you see depicted here, which will be based on monolithic active pinset sensors like the ones that were mentioned before are being used by STAR and also will be used in the next runs of the ALICE experiment. And you see here, let's say, a flagship measurement of why we should go to this. This is the signal to background ratio for the D0 as a function of the efficiency of your selection. And you see that moving from the hybrid technology that was used in all the LHC experiments during the run 1 and run 2 to the MAPS allows a dramatic increase of the signal to background discrimination. So how did we do the performance studies? So we used a fast simulation tool and we worked for the central lead collision, which is the most challenging environment for such a reconstruction. So we took the NDPT and the NDY shapes from POWER plus PCS simulations. Here you see the rapidity distribution that are predicted by POWER for the different meson species. As already touched in the previous talks, there is at SPS energy a significant difference between particles and antiparticles. Then we need to simulate also the background, which is a huge one. And for this, we used the NDPT and the NDY measurements by NA49 at top SPS energies, which exist for pions, kaons, and protons, which are the most abundantly produced particles. And we took the parameterization from this paper. And then we plugged all this particle into a parameterized simulation of the resolution of the vertex telescope detectors. The vertex telescope, as I anticipated before, is based on MAPS, large area maps with stitching technologies. We are currently optimizing the geometry and the number of planes. So we did simulation with 5 and up to 10 planes in order to find the optimal configuration. The thickness is 20 microns, so order of 0.1% of interaction length for radiation length for each plane, and a resolution of the order of 5 micron based on this pixel size. And then the tracks are reconstructed using a fast Kalman filter approach, and this allows then to reconstruct the meson decay vertex from the decay tracks. So here we see some plots showing the fraction of mesons which fall in the acceptance and are reconstructed with the tracker for different configuration. The bluish colors are the simulation with 5 layers, and the reddish colors with 10 layers, and different requests on the number of hits in the telescope. And essentially, you see that we have quite a large rapidity coverage. And in the right plot, you see one of the crucial quantities for the discrimination, which is the resolution on the position of the decay vertex of the D0. And you see that we can reach resolution of the order of 10-15 microns with all the different configuration that we tested so far, which is good enough to separate the decay vertex from the interaction point. And so one can apply geometrical selection based on these displaced decay vertex topologies. As you see here from this efficiency plot, you see the green points is the fraction of D0 mesons that after having been reconstructed pass the selection. So the selections, the geometrical selections essentially keep 30% of the D0, but allow to dramatically increase the signal to background, which before the cuts is at the level of 10 to the -7, and after the selection is of the order of 1/2. And they are based essentially on the distance between the interaction point and the primary vertex, the pointing of the decay tracks of the D0, and the pointing of the D0 momentum to the primary vertex. Of course, nothing is really optimized. We just use few variables to demonstrate that the analysis is feasible. Then to have performance plot, one needs to normalize the signal yield per event. And for this, we used an assumption on the charm production cross-section, which, as I mentioned before, is not measured at SPS energies. And we used the root S dependence predicted by PQCD calculation. Then we used, of course, the nuclear overlap function from Glauber. And then we needed also an assumption on the fragmentation fractions of the charm quarks in different charm hadron species. And as already mentioned before, these fractions are significantly different between E plus, E minus, where you see, for example, we have 60% of D0, and PP at LHC energies, where this fraction goes down to 40%, while correspondingly there is a increase of the fraction of baryons. So at the moment, we use a sort of average of these two values, but this also is a point that makes very interesting measuring these fractions also at SPS energies. So with these numbers, we could build some plots that show the performance for the D0 reconstruction at two different energies of the beam energy scan. Here are the expected invariant mass distribution, which essentially show that we would have a spectacular significance for the reconstruction of D0 from its k pi decay, which translates into a statistical precision better than the percent level, which allows for differential study of yield and V2 as a function of PT rapidity and centrality with the NA60 plus apparatus. And we started then to go to more complex and more rare mesons. So I show here some studies of physics performance for the DS mesons. This is more challenging than the D0 because it has a three-body final state, so much larger background. And again, we didn't do a real optimization of the analysis, but rather we exploited few variables. So namely the fact that the decay into the KK pi occurs via phi resonance states. So we use the invariant mass of the two kaons, which in the case of the signal, which is the blue, is peaked at the phi, while at the phi mass, while in case of the background as discontinuous. And then again, we exploited the pointing of the tracks to the primary vertex, a combination of these impact parameters, the decay length and the pointing angle. And as you see, for all these variables, we have a significant separation between the signal and the background. And when we play a sort of tuning of the cuts, you can see that we can reach signal to background ratios better than 1%, even using only these few cut variables, keeping the efficiency at the level of 30%. So we have a good working point that projects into this kind of performance for the invariant mass distribution of KK pi pairs, where you can clearly see the peak of the D sub S with a significance that would allow a measurement at the percent level with this very, very rough tuning of the cuts. So we are very happy with this. And this essentially confirmed that out of these, our, let's say, preferred four guys that we want to reconstruct, we will be able to measure D0 and DS. And this also tells us that the D plus will be within reach, because you see it as a larger branching ratio of the D sub S and also a longer lifetime. So this will be easy to reconstruct, well, possible to reconstruct. So now we are performing studies for the most challenging situation, which is that of the lambda C, which we are studying in the PK pi standard decay channel, but also we are planning to have a look in decay channel which have smaller branching ratios, but could profit of the high purity that we could have on the K0 short and the lambda reconstruction, which can be reconstructed from the V0 decay topology. And so for this, we started an effort to do fast simulation for the reconstruction of lambda and K0 short. And as you see, we have a very good purity and very good significance for the reconstruction of lambda and K0 short, which we want to exploit for the lambda C baryons to complement the measurement in the PK pi. But also you see here some very fresh simulation that will allow also to access cascade, and we expect also omega hyperons. And this opens the last 2 minutes, I guess, of my talk, just to motivate that NA60 plus will also be able to perform studies of strangeness productions, which will be interesting per se, not only as a tool to construct the lambda C, because they could complement or extend also the measurement of NA57 of the yields of hyperons as a function of wounded nucleons of centrality, and also putting more PA points here. And also we could extend the measurements of NA49 of the anisotropic flow, which exists for the lambda as a function of PT for a wide centrality range via precise measurements of hyperon Vn coefficient, and also extending to psi and omega. And finally, I touched the phi in the reconstruction of the D sub S, but we could also perform measurements of the phi in the KK channel in addition to the immune channel, of course, and this shows the improvement of performance. This is the invariant mass distribution of phi to KK that was obtained for the NA60 experiment, and it was possible to measure the phi only for PT larger than 0.9 GeV, while with Na60 plus, this is the projected performance. We should be able to go down to 0 with a much better resolution, measuring order of 10 to the 10 5 mesons. So this brings me to the summary. So I hope I demonstrated that we have a strong physics program to measure open charm with Na60, and we have also a detector which will allow to perform very good measurements that could provide important information to characterize the transport properties of the QGP at large mu B. And I showed some first studies for charm mesons, and what is ongoing is the study for charm bios, and also to consolidate this first estimate that I have shown for D0, D sub S, and for the strange hadrons. So that's it, and stay tuned because Na60 plus is moving on. Thank you.
Thank you, Francesco, for this very nice overview of the capabilities of Na60 plus. Questions?
Yeah, so this is really beautiful. I'm totally impressed. You know what you can do. I mean, you know, with this we get a charm transport coefficient. It's fantastic. How low? I mean, I suppose you showed mostly the 17 GeV results. Is that true? Or so how would it suffer if you go all the way down to 6 GeV?
Okay. Yeah. The only result for open charm that I showed at a lower energy is this one. So the only study that we have so far is for 10 GeV, which corresponds to 60 GeV of beam energy. And with this assumption, because here it's crucial to point out that we have really a wide uncertainty, a very large uncertainty of what could be the total charm cross-section. So with the assumption that the cross-section will be of 0.5 microbars, at this energy, we would be able to perform a measurement with good significance. But of course, let's say, we could go down to a cross-section of the order of a few tens of microbars, whatever the root S will be that provides us with this cross-section. Yes, we would have a % precision on the PT integrated measurement, which could mean that we could do few PT beams. Now also the spectrum that become very steep, and also for the spectrum we are trusting the shapes given by POWEG. So yeah, with a number of uncertainties, but few points could be measured.
I have few, but maybe very technical points still would like to ask. So I understand if you look, for example, to the phi decay to K plus, K minus, so similar mass of the particles, then I understand how you reconstruct your invariant mass. So in the case you have K pi decay, what do you do then?
We don't have PID.
Yeah,
so
exactly.
Essentially, with all possible pair combinations, and
then we assign mass just...
yes, for example, in the case of the D0, so now let me put some examples. So in the case of the D0, we do all the possible opposite sign pairs, and we assign two mass hypotheses. Okay, the case of the D plus is easier because you see, once you have the charge, you also have the identity because the kaon is the opposite
and then
sign.
Okay, good. So I understood.
So we do all the mass hypotheses.
Can I just one more only, or I have to decide which one to ask? Yeah, maybe to this 5 versus 10 layers of the microvertex detector. So if you can bring the slide where you show this efficiency.
Let me remember where it was.
Like this one. So from this particular plot for D0, one would essentially conclude that 5 layers is just sufficient to use. So what would be your final choice of the signal that will decide for you how many layers you want to use? Would it be lambda C or?
Well, so first of all, in this simulation, there is an assumption that everything is fully efficient. So one point from the experimental side is that 10 layers means redundancy. The second point is that crucial, let's say, will be mostly the studies of hyperons, because the decay length of the open charm mesons will always be smaller than the distance between the target and the first plane. But this is not the case for example, the lambda and the k0. So having more layers buys you some decay distance, so a larger efficiency.
Okay, so
hyperons.
redundancy is the right word.
But
Okay.
yes, in the case of open charm, redundancy is the crucial thing.
And I was allowed for the last one? Okay, good. So when you do the fast simulation, I understand you do the background and analysis of the background and analysis of the signal in the separate way. So actually same true for the dilepton signal. But of course, the efficiency of the signal reconstruction can be reduced if you do embedding of the signal into the background of the event. How do you take into account this effect?
The simulation of the signal includes a simulation of the occupancy of the planes based on the background. So the tracking is done in an environment in which the number of hits in each of the planes is realistic.
Mm-hmm. Okay, so this is fine with respect of the occupancy on the detectors,
Yes.
But then, for example, if you want to, I don't know, detect one of the topology of the decay by using, I don't know, kick in the field or whatever, then I would assume one would need rather the full simulations.
Yeah, of course. At the end, we will need the full, but yeah.
Okay.
Okay, we had also one question from our online participants. Shindong, I think you had a question.
Thank you, Chair. Yeah, thanks for the nice presentation. I just one technical question for the MAP sensor. What is the event rate you're looking to now? And can the MAP sensor can handle this rate? What technology you're looking at can handle this rate?
So for the technology, we are let's say we are counting on a strong interplay with the new layers, the new inner layers of the inner tracking system of Alice. So to use the same stitching technology, which provide large area maps, and so to have a synergy with that development. The other question, sorry.
What is the event rate you'll be looking to?
So the interaction rate is very large, but I think what is relevant here is the readout rate at which we want to take data, because we essentially collect minimum bias collision with the detector. So I don't remember the number of the readout rate, but maybe 200 kilohertz is the interaction rate. But yeah, maybe Gianluca, you can comment on this.
What matters in the end is the particle flux, so the kilohertz or megahertz per square centimeters. And so for that, we did a complete simulation based on FLUCA, which includes also delta rays, which give a non-negligible contribution. And it is around, for the beam intensity that we are considering, is around 5 to 6 megahertz per square centimeter in the innermost regions, because it is highly non-uniform as a function of the distance from the beam axis. And this should be okay if you compare to ALICE ITS3. ALICE ITS3, if I remember well, is 3 to 4 megahertz per square centimeters. Already Alpide was designed to work, if I remember well, up to 10 megahertz per square centimeters. So it should be okay.
Great, thank you.
Okay, thank you. Let's thank Francesco one more time. And then we have one last presentation in this session by Min He on non-perturbative open heavy flavor transport in hot QCD matter. Okay, you can share your screen, please.
Sure. Hello, can you see my slide?
Yes, we can see your slides. Thank you.
Okay. So let me start. First, thanks to the organizers for inviting me to this seminar, to this workshop. I'm going to talk about heavy quark statistical hydrogenization in high energy PP conditions, which is a bit different from my preliminary title. This may be not quite about the high mu B regime, but finally I will make some outlook in this connection. So here the basic idea is that charm statistical coalescence is very likely in a quark-rich environment, like the environments created in high energy PP conditions. Thereby, relative chemical equilibrium could be well achieved between different charm hadron species according to their statistical weights. Here, one important thing is to augment the charm baryon spectrum listed in PDG with much more states as predicted by relativistic quark model calculations. We're going to first deal with the minimum bias PP conditions, in which the quantum charges can be treated as being conserved on average. So this will be done in the grand canonical version of the statistical hydrogenization model. But going to low multiplicity PP events, quantum charges need to be strictly conserved. This can be done in the canonical version of the statistical hydrogenization model. Recently, this was also generalized to the bottom hadron sector. I will be showing also some preliminary results in this regard. So first, the lambda C to D0 ratio in minimum bias PP conditions. Alice measurements had showed a pretty large lambda C to D0 ratio in high energy PP conditions, much higher than the typical value as measured in E plus E minus conditions. And in statistical model calculations, like by Anto and his collaborators, when including only the PTG list of charm hadrons, in particular charm baryons, they predicted the lambda C to D0 ratio as to be like around 0.2. And PCR, to explain this puzzle, this larger ratio, PCR8 introduced the color reconnection mechanism, which is also to enhance the baryon production. But here we're going to do it in an augmented version of the statistical hydrogenization model. We noted that in PDG there are only few charm baryons that were already measured. But relativistic quark model calculations predict many more. So, and this was also supported by lattice calculations. So we just took all these charm hadron spectra as calculated from relativistic quark model calculation, relativistic quark models, and calculated their thermal densities in the grand canonical version of the statistical hydrogenization model. We take the hydrogenization temperature as 170 MeV. This table shows the thermal densities comparing PDG and RQM charm spectra. We see, especially for the lambda C, the density is almost doubled from PDG to RQM. As a result, the ratio of lambda C to D0 also almost doubled, getting already quite close to what Alice data shows, around like 0.55 or 0.6. Here, the strangeness suppression factor 0.6 was used, and for the strong fit downs of the excited states in this table, we assumed that the branch ratios of all excited lambda C and sigma C's are like 100% when they decay into the ground state lambda C. Then, in order to calculate the PT differential cross sections, we take the phono charm PT spectrum and perform the fragmentation charm quark into all kinds of charm hadrons, including all excited states. And in this fermentation, the relative weights between different charm species are determined by the calculated thermal densities. The final step is to perform a decay simulation of all excited states to the ground states. This way, we can obtain the ground state charm hadron spectrum, PT differential cross sections, like for D0 and DS, and then the ratio of DS to D0. We see for these charm hadrons, both PDG and RQM are working pretty well. But of course, the fitted charm cross sections will be different. Within PDG, the charm cross section per unit rapidity was 0.85, and with RQM, the cross section is 1 millibar. But then going to charm barons, we see the lambda C indeed favors the RQM scenario with a larger charm cross section. Look at this ratio, lambda C to D0. In particular, this enhancement relative to the PDG as shown by this green curve. The enhancements at low PT is simply due to the feed downs of the excited charm barons augmented from the RQM. This uncertainty band is due to the branch ratio uncertainty for the excited lambda C and sigma C above the DN threshold when they decay into the ground state lambda C. We take this branch ratio to be like 50 to 100% so that we get this band. Actually, the Alice data was updated, and the data was brought down actually closer to our curve. And in this approach, the sigma C to D0 ratio can be also accounted for with the uncertainties, but the cascaded C to D0 ratio was much underestimated. Although this value from statistical model calculation it's already twice as large as was PCA8 obtained. Okay, so that was part one. Now part two, system size dependence of this ratio lambda C to D0. Alice also measured this ratio in different multiplicities, charged particle multiplicities. You see, indeed, with increasing charged particle multiplicity, this ratio is also increasing. This might be straightforwardly consistent with the statistical coalescence. I mean, imagine a charm quark recombining with surrounding light quarks. Then the lambda C to D0 ratio would be proportional to the density of the charged particles. So we're going to tackle this in the canonical version of the statistical translation model, in which we're going to conserve the quantum charges in a strict way. This is the canonical partition function with charges, electric charge, baryon charge, strangeness, and charm number. We see if we just look at the canonical partition function as function of the baryon charge put in the system, then it's decreasing. It's like a step function with increasing baryon charge. This is because once a baryon is created, then simultaneous creation of a anti-baryon should be required in order to fulfill baryon number conservation. Of course, this is very expensive in terms of energy. So one obtains this chemical factor comparing the canonical version and the grand canonical version of this hybridization model. This factor is to characterize the canonical suppression for a charged hadron field when its quantum charge is not zero. Now look at more details of this chemical factor in a more quantitative way. First, looking at this column at a given volume, we see the chemical factor is progressively smaller for hadrons containing more charges. They all contain the common charge number, the charm number, but you look, for example, this DS contains additional strangeness, and this cascade C contains both strangeness and charm, and also baryon number. So its chemical factor is even smaller. For this row, look at this row. The chemical factors indeed is increasing with volume, finally tending to the common residual canonical charm suppression for all particles at a large volume. Then the relative chemical factor, the lambda C to D0, and the DS to D0. This relative chemical factor is also increasing with volume, and finally tend to unity, because you're just left with their common charm suppression. Finally, we calculate the densities of all these ground state particles with fit-downs. Also looking at this lambda C, the density of each charm hadron is increasing with volume. And then the lambda C to D0 ratio and the DS to D0 ratio showed a marked system size dependence from small volume to high volume, from canonical limits to grand canonical limits, which represents like a 40% reduction from the large volume to like 10 to a small volume 10 Fermi cubed. So this naturally explains the system size dependence of these ratios. Finally, we want to convert this ratio into a PT dependence. So we see this lambda C to D0 ratio. There is a splitting of lambda C to D0 between small multiplicity to higher multiplicity. This is simply due to additional canonical baryon suppression on charm baryons, which becomes stronger toward smaller system size. There's also a similar splitting of DS to D0 ratio because of the additional canonical strangeness suppression on DS metal relative to D metal. Okay, now part 3. This calculation was recently generalized to the bottom sector. So we're going to deal with the lambda B to B metal ratio in minimal bias PP conditions. For bottom hadrons, there are just very few particles that have already been measured with and listed in PDG. And RQM, red physical quark model calculations, predicted many more, not only for baryons but also for metals. So we took all these bottom hadrons and calculated their densities again in the grand canonical version of statistical hydrogenization model at still the hydrogenization temperature 170 MeV. We see compared to the PTG, RQM gives like 20% more B metals. And for the baryons, for example, lambda B and the cascade B, the density is almost doubled again. Converting these densities into ratios, we see the BS over B minus, this ratio actually is a little bit reduced from PTG to RQM. But the baryon to metal ratio, lambda B to B minus ratio, it's enhanced by, I think, more than 80%. In this calculation, again, we used the strangeness efficacy 0.6. And for the fit downs of all excited states to the ground state particles, I mean the systematics of the branch ratios, we made a kind of systematic estimation. Look at these diagrams. We just count all possible diagrams once a channel opens up. I mean, above the allowed threshold, then we count its pertinent diagram. But we note the probability of producing a QQ bar pair from vacuum should be different for light quark pairs and strange quark pairs. So we assume this probability is proportional to this exponential factor. This is the hydrogenation, TH is hydrogenation temperature 170 MeV. Then we get this this probability ratio between producing a pair of light quark and a pair of strange quark, 1 over like 1/3, using the typical quark methods. This means the diagrams involving SS bar should be counted as 1/3, not 1. This way, we can make an estimate of the branch ratios like a typical excited state of P meson. It decays to the B plus height 0, and there could be also some up channels. So we made a systematic estimate for all excited states. For baryons, it's also like this. For baryons, just count all possible diagrams, and diagrams involving SS bar it's counted at 1/3. As shown for this typical lambda B, the excited states of lambda B. It can have all possible decay channels. Then we calculate the branch ratios just by counting the diagrams. The result obtained here is actually consistent with some results, very limited results computed in some quark models. So unlike the case of charm hadron calculation, here we just use these estimated branch ratios. So we don't have finally we don't have an uncertainty band. Okay, so in order to calculate the differential cross sections, PT differential cross sections, we again take the phonon B quark PT spectra and then perform a fermentation simulation into all kinds of excited states, and finally perform their decay simulations into ground states. This way, we got the PT differential cross section for P meson and also lambda B. We see the 70 and 30 TeV data are better fitted than the 8 TeV data. Of course, in this calculation, we use the same parameters. I mean, the parameters in the fermentation functions. In this so-called alpha fermentation function, the alpha parameter for meson was taken 45, baryon 8. And in this way, we also fitted the baryon cross section at different energies at forward rapidity. Finally, we can convert the PT differential cross sections into PT dependent ratios, charm hadron chemistry. So this is the BS to B meson ratio, and this is lambda B to B meson ratio. We see these both ratios are almost unchanged from 7 to 30 GeV. In both ratios, the PDG only curved. This dashed curve and this dashed curve, PDG only curved the far off data. In both cases, the RQM states are needed, as shown by these solid curves. Okay, my summary. So in high energy PP collisions, we showed that heavy quark hadronization into open active level hadrons may well be of statistical nature, but the PDG list of heavy flavor hadrons must be augmented by additional states, and their PT dependence hydrochemistry ratios can be decently described. this workshop is about high mu B region. So at low energy, high mu B region, I think we can expect an interesting splitting between the lambda C to D0 ratio and the antiparticle, antibaryon to D0 ratio. And especially, we need to develop a non-perturbative charm transport approach. First, calculate the transport coefficients at the high mu B, and also should develop a medium evolution model, for example, hydro as high mu B, in order to tackle the charm transport in high mu B QGP plus hydrogen reactor gas liquid. Okay, that's it. Thank you.
Let's thank Min for this nice talk. Questions, discussions? Ralf.
Yeah, I mean, so a very impressive result for the bottom hadrons, which I haven't seen yet myself. And I was really also intrigued by the way you estimate the branching ratios. I was wondering if that way of estimating those would offer any advantages in the charm sector.
Sure. This is something I want to revisit for our charm hadron calculation.
Okay, thank you.
This should be done in a more systematic way also for charm hadrons.
Thank you. Any further questions?
Hi, so my question is to your almost last slide when you talked about actually the anti-lambda C. So when you go to high mu B, I mean, this of course sounds interesting, but then of course also I mean, you have mostly baryons and no antibaryons down there. So if you already have problems with the lambda C, how would you get the anti-lambda C there?
Yes, of course, there should be more baryons than antibaryons. What do we mean by saying that we already have problems with the lambda C?
Well, I mean, in terms of statistics, right? So if you go to high mu B, means you have lower energies, means you have already, you need a lot of statistics to get even the lambda C. And then you have the problem that you have many more baryons and antibaryons, which means that on the one hand, the lambda C goes up, right? Or the lambda C to D goes up because you have more relative lambda C's, but your anti-lambda C should drop also as with increasing mu B. So, I mean, one has to look into this, whether this actually makes sense or there are really too many orders of magnitude difference here.
Okay, so this is about
okay, we have one question from our online participants, Johanna Stachel.
Yeah, I have one comment and one question. My comment is that indeed there were many newly discovered states, charm and beauty states at the LHC, but there were relatively few simple charmed baryons. I think there was only one additional lambda C. There was 3 or so cascade Cs, 2 cascade Cs and 5 omega Cs, right? And this is what is included in the PTG in 2020. So unfortunately, these gazillions new states, they exist also in lattice QCD, although there the energies are a bit or are higher than what is used in the relativistic quark model. So it makes me uneasy to think that all of these states should exist, and yet none of them are seen.
Okay.
So of course it could be that also the LHCb people are not searching very systematically for these because it is not the main interest. But I think I would feel a lot more comfortable if some more of these states were discovered. Now, my question was on the canonical suppression to explain this multiplicity dependence. That was probably a bit fast for me. I understand what you write down in terms of these gammas and so on, and then you have basically a canonical partition function. But then how do you obtain the values, this gamma C or gamma S in particular for the gamma C? I mean, you are bounded by an external input, right? You have to use the charm cross-section for this multiplicity. And so for the charm, other than for baryon number or for strangeness, the canonical suppression comes in a different, it comes in only via the back door because the number of charm quarks is already fixed. Is that what you are doing or not? I mean, that's what we do.
Okay, first let me reply to your comments about the missing states. I mean, we don't know if family system maybe finally in future could tell us more about if we have its state or not. But if we just replace the charm quark with the strange quark, I mean comparing the charm sector with the strange sector with the same quantum numbers, we do have many more strange baryons. So why not for charm baryons?
Well, as an experimentalist, I would say we need to discover them. But could you?
Sure.
But my other question: what is the role of the gamma C, and do you fix the total charm quarks in the system? I mean, they are given by the charm cross section, right?
No. For gamma C. For gamma S, that we did for the minimum bias, we just take gamma C equal to 0.6. It's just parameter. And for gamma C, actually we took like around I remember like 16 or to 20, which is a generalization of your statistical model applied to like lead collisions, AA collisions, but in the limits of lower multiplicity. Yes, but numerically, let me tell you, numerically, how large the gamma C is, it's not quite relevant in numericals, because the charm number density, the total charm number density, finally, it's a very small value. We checked, it's not the final results. For example, the ratios, it's not sensitive to this.
But your whole multiplicity dependence comes from that, right? You say the multiplicity dependence is a canonical effect.
Yes, it's a canonical effect. Yes, it's a canonical effect. It's just additional, just because the lambda C contains except for their common charm, lambda C contains another baryon number. Yes, contains another strangeness. Simple, very simple.
Well, it's too simple for me, obviously. We need to settle it offline.
Yeah, maybe you can settle that offline. I remember, Francesco, you still had a question. What? One last question.
Yeah, it's on this slide. So I was wondering, it seems from the numbers that I looked by eye that the relative increase with multiplicity of the lambda C over D0 and the DS over D0 is the same, about 50% from let's say the lowest volume to the largest one. And this is, let's say, from the measurements that we have so far, this is a bit at odds, because the DS over D0 that we measure, it seems flat in the PT range that we covered as a function of multiplicity. So I was wondering how strong is in your approach that the two ratios should have the same trend with multiplicity.
Sorry, you're talking about the PT dependence, the shape of a PT dependence, or?
Well, the dependence of this ratio of multiplicity. Of course, we don't have the PT integrated one, so we should base our conclusion on the measurements on the PT range that we measured. However, in the PT range that we could cover with the measurement, the DS over D0 is flat with multiplicity in PP, while the lambda C over D0 increases.
Okay, this This I don't know. You're saying our prediction for the DS to D2 ratio is not supported by data. Right?
Yeah.
We do see a strong, a marked system side dependence also for DS over D0, but this is not seen in data. You're saying that, right?
Yes. Okay. We'll keep that as a comment. Okay, so let's thank all the speakers of the first session again.
Thank you.